This is part 2 of infinite limits and limits at infinity, and we are now talking about this idea of limits at infinity. So as you are going way out towards infinity, what is happening here? We are kind of trying to describe our behavior at the ends of our graphs. So what is happening here as we go to infinity? This function here is quartic. Two squared terms, when you multiply it, it's going to be a quartic polynomial. And our leading coefficient is a positive 1 when you multiply this out. So quartic functions, like quadratic, they have very much a similar shape. And with that positive leading coefficient, they're going to be rising really at either end, but we're concerned with on the right. So like a quadratic function, this is going to be rising to the right. So as you go way out to infinity, the end behavior or the limit is going to be infinity. Here's another. Now we're working with a cubic function, and what happens when you're working with cubic functions and you go way out to the left, way out to negative infinity, what is the end behavior there? Well, cubic functions with positive leading coefficients, they are shaped like the part B from the end behavior discussion that we saw just in that end of the previous video. So what's going to happen is it's going to fall to the left, which is what we're concerned with, and it would be growing to the right. Which means if you're looking way out towards negative infinity, well, in this case, because of our leading coefficient, it will also be negative infinity. Let's look at another example together. We have here a rational function, and when it came to rational functions, we want to look back at our notes for those rules. We have the degree of the numerator equal to the degree of our denominator. So there is a horizontal asymptote at the ratio of our leading coefficients, those highest degree terms, the squared terms. So that would be 3 over 1, which is just 3. So the graph goes to 3 as your x value is going to infinity, which means that our limit is 3. Last part here in this example number 4. Again, another rational function. And in this case, we are bottom heavy. The degree of our denominator is larger than the degree of our numerator. In this case, there is a horizontal asymptote at y equals 0, which is the x-axis, as your x value goes to negative infinity. Which means that our limit here would also be 0. Okay, now going to our last page here. I want, because you're probably, after looking at those last 2 examples and looking at those rules, you're wondering why these rules are true for finding horizontal asymptotes. And where did these rules come from? Well, I want to kind of address that in this next part. If you look at example 6, The instructions there say divide every term in the rational expression by the highest power of x that appears in the denominator. Then apply the properties of limits to evaluate each piece to find the limit at infinity, which is our end behavior. We're looking at the graph. We kind of are already seeing what is going to happen, but we're going to justify our steps algebraically here. So we're going to divide by the highest power of x that appears in our denominator. We're going to divide every term by that. And that would be by x squared. So every term is being divided by x squared. And this is appropriate. You can do that. We're not changing our problem because we're doing the same operation to every single term. Now, when you simplify, you would have 2 minus 10 over x, all of that divided by 1 minus 8 over x plus 15 over x squared. Now, we are trying to figure out what happens as x goes to infinity. Now, let's just think here for a moment. What does infinity mean? Infinity means a really unimaginably large number. So, ladies and gentlemen, if you put 10 over a really large number, what happens? Think about that for a second. 1 over a huge number is really just 0. It essentially is 0. So what we're doing here, we're kind of manipulating our problem within the laws of mathematics so that we can begin to understand what is happening at these just huge, unimaginable numbers. This would really be 2 minus 0 over 1 minus 0 plus 0, which is just 2 over 1, giving us 2 as our limit as you go to infinity. So this kind of validates that second rule that we saw, where if the degrees are equal, just take the ratio of your leading coefficients. It would be 2 over 1, but this helps to validate why that is true. Here's another one. Now we're bottom heavy, and we're going to validate why it is that the result, why we're able to kind of take shortcuts. So what happens here? We're going to be dividing by x squared because that is the largest or the highest power of x that appears in your denominator. And then we'll simplify, so that'll be 1 over x plus 3 over x squared. All of that divided by 1 plus 4 over x plus 5 over x squared. And now we're going to pretend that we are substituting in infinity. 1 over infinity is 0. 3 over infinity is 0. 1 plus 0 plus 0, that really is 0. 0 divided by 1 is 0. So when you are bottom heavy, the limit is 0. Well, that occurs and is validated in this example algebraically. The third type of scenario is when you're top heavy, when the power in the numerator is more than that in the denominator. Here, the highest power in our denominator is x, and we're dividing now every term by that. When you simplify, it'll be x minus 4 minus 3 over x. All of that is over 1 minus 2 over x. When you plug that in, you'll have infinity minus 4 minus 0 over 1 minus 0. That's really like infinity over 1, and infinity over 1 is infinity. So this helps us to understand our in behavior here. As you go to infinity, what's happening? We don't really have a limit. It's going to infinity. We have this, what is called a slant asymptote. So it's not restricted. It's going to be going upward forever. So functions with horizontal asymptotes. That is going to happen when the limit of your function as you go to infinity or negative infinity is a real number, is a b that is an element of the reals. And the line y equals b is your horizontal asymptote for the graph f of x. Slant asymptotes occur when you take the limit of your function as it goes to infinity, and it is in fact either positive or negative infinity. And you would use synthetic division to find the equation for your slant asymptote, and then test values to find out what that in behavior truly is. So the definition, the proper definition, the limit definition for a horizontal asymptote is if your limit as you go to, that should be infinity, not a. As you go to infinity or as you go to negative infinity is your b value. And that b value is your horizontal asymptote of the function. So the limit of your function as x approaches infinity is b, or the limit of your function as x approaches negative infinity is b. That is where your horizontal asymptote will be occurring. Last example here. We're going to use algebraic techniques to find the limits for this g function. Now, we already can see these limits graphically here, but we're going to use algebraic techniques. Now, in red there, I've reminded you of something. X, when you take the square root of x squared, that's really the absolute value of x. So this is kind of maybe different. This is a different scenario. Yes, in that denominator, we're going to divide those terms by x squared, but really that is the same thing as the absolute value of x. So we're going to divide in our numerator there by x. That reduces to 3 minus 3 over x, and in the radical you'll have 1 plus 4 over x squared. If you're substituting in that infinite amount, it would be 3 minus 0 divided by the square root of 1 plus 0, which is really just 3. Now, if you were coming from the left, or you were trying to find, if you were going towards the left, trying to find your limit as x approaches negative infinity, you're working with negative x values. That's going to change the signs here of every single term when you divide by that negative x. So you'll really have a negative 3 plus 0, and inside the radical, that would be 1 minus 0, which means that as you're approaching negative infinity, the limit is negative 3. And we see that happening graphically here. The limit there, that horizontal, that in behavior, is negative 3 as you go to negative infinity, and it is positive 3 as you go towards infinity. So ladies and gentlemen, that is all that I have for your infinite limits and limits at infinity. I hope now that you see that they are in fact two different ideas, and I'm looking forward to talking about them more with you. That's all. Have a good rest of your day.